Okay, so we were discussing feedback systems. We're still in the block diagrammatic stage, and in this class we'll graduate from the block diagram to a circuit. But before that, let's talk about some things which we haven't yet talked about. So we were trying to, draw an analogy between the classical block diagram of feedback systems using G, H, and all with the one that we were interested in. And the stuff that we were interested in was this. Okay, so now if I have to draw an analogy between the stuff on the left and the stuff on the right, and given that I know that V naught is 1 over H GH by 1 plus GH, or more popularly, equally popularly abbreviated as L by 1 plus L. Okay. So how do I figure out what is H and what is L in the network on the right? What should I do? So which one do I want to, would you want to explore first, H or L? H, let's do H. So in order to figure out H, what should I do? What is the test? You can do L first? Okay, let's do L first. So fine, in order to do L first, what should we do? No, you don't need to take any approximation. I can figure out L. What is the procedure to figure out L? Right. So you have to break the loop. First, break the loop, desensitize the input. Right. So if I desensitize the input, I desensitize the input. So I need to break the loop. I can break the loop here. I can break the loop here. In this diagram, it really doesn't matter where you break, but in general, there is a constraint. But let's assume we break the loop here. And we apply a phase voltage here. And what should I be looking for? Return voltage, right? I should be looking for V return. So if I can express V return in terms of V test, then the ratio of V return over V test, negative of that, is the loop gain, right? So what is the loop gain in this case? A by K, right? Loop gain is A by K. Now that we know loop gain, let's say we want to figure out H. How will you figure out H experimentally? L tends to infinity. Great. So if L tends to infinity, what will happen to the closed loop system? By the way, L is independent of where you have applied the input, right? Because as you can see, L is G times H, and G and H are independent of where you have applied the input. And in the way we have done it also, that we distorted the input or desensitized the input and done the calculation. So what about H? Is H independent of input or H is dependent on input? Is dependent or independent? Can't hear. So to speak aloud. H is independent. Why do you say H is independent? Okay, so let me, okay, H is independent of input, I agree. But what I essentially meant was, so limiting value of V naught by Vi when L tends to infinity, whatever you get, happens to be 1 over H. But is this guy independent of input? Yeah, I agree. H is a part of the network. H is not independent of input. But V naught over Vi, is that independent of input? Or dependent on input? By this, I mean where the position at which you have applied the input. It depends on position. So GH is not dependent on position. But limiting value of V naught over Vi when L tends to infinity depends on position. So which means you have to go back to the, we have to find H, you have to go back to this network. Okay. So now, what test should I do to find out what is the H? Because in most networks, you will not have block diagrams of G and block diagrams of H. Right? So you have to, from whatever has been given to you, you have to derive, or you have to come up with a way of figuring out what is H. So experimentally, what should I do? We talked about it in the previous class. So is this constraint easy to impose in our network or difficult to impose? Okay, so when I say, so let's think about it, right? So what is it that is causing the difficulty of figuring out H from this block? Yeah, correct. Like, so this is, you are right. What he is essentially saying is V naught, here I will have V naught over K. So looks like the feedback factor is 1 over K. So H seems to be 1 over K, right? So which in fact is correct. But again, very often what you will see is you will have a whole bunch of stuffs connected here, some bunch of stuffs connected here, and all those things will happen, right? So it will not also be quite apparent what will be H in any generalized network. So we need to develop a framework to figure out what is H. And we talked about something in the previous class. What happens to a negative feedback loop when the loop gain tends to infinity? Can you repeat again? VE tending to 0, great, right? So this is VE. If you can identify that node in the network, which is the error voltage. So if loop gain tends to infinity, that error voltage will go to 0. Provided we are taking the error in voltage domain. If you are taking the error in current domain, then it has to be current going to 0. But we will not be dealing with those type of circuits. We'll be dealing with cases with where error is the voltage. So let's limit ourselves to that constraint that if you can find out what is the error voltage, all you have to do is set that voltage to 0 and then work backwards. So if I set this to 0, so what is the consequence? Pardon? Output will be constant, but if we don't want to go this direction. So we will go in the other direction. So what is the feedback voltage supposed to be then? It is supposed to be Vi. If feedback voltage is supposed to be Vi, what will be V naught? It will be KVI. This is Vi, this is KVI. Right? So now if I turn our attention to this constraint, so this is K. Right? Then what is H? 1 over 2. Right? So this is essentially the framework, right? So you identify, I mean, it's easy to identify a loop, and it's fairly easy to identify which is the error amplifier, or which is the amplifier, which is the block that is amplifying the error. So in order to figure out what is the feedback factor, or in order to figure out what is the expected operation of the circuit, all you have to ensure is that the loop gain tends to infinity. If the loop gain tends to infinity, you know that error voltage goes to 0. If the error voltage goes to 0, you work backwards. Okay, so this way of expressing loop gain, expressing the transfer function is quite popular, because essentially what is this saying? This is saying that if the loop gain tends to infinity, I am supposed to get this, right? And you design your circuit in assuming that we are supposed to get this. Everything else is an error, but you should be able to easily identify what would have happened if you are supposed to get what you are designing for, right? So that's why this way of expressing your V naught over Vi is quite useful and quite popular. Okay. Okay. Any questions? Yes.
When you say that when loop gain tends to infinity and error voltage goes to 0.
Right. Okay. So let's say error voltage is not 0, right? So it's better to explain in that way. So the question is, when the loop gain tends to infinity, why is the error voltage going to 0? So let's say the error voltage is not 0, right? And the loop gain is infinity. Okay. So what is V naught over Vi, or let me write it in this way. So V naught is G times Vi minus V naught times H, right? So if I write, so I know that V naught is G by 1 plus GH times Vi, which is 1 over H L by 1 plus L times Vi. So what is V naught over Vi? If I use this term, V naught minus Vi. So let's assume V naught is this, right? So what is V naught minus Vi? No, right? V naught minus Vi is what? In this case, when the loop gain is not infinity, V naught is not exactly equal to what you expect. I missed term. No, yeah, right. So what is V naught over Vi? So V naught is G by 1 plus GH minus 1 times Vi. So this becomes, oh, something is wrong. Oh no, it's fine. Oh, sorry, I'm making one mistake after another. So V naught is G times VE, where VE is Vi minus V naught times H, which is so what is VE? VE is V naught by G, which means Vi by 1 plus GH. Right? So when loop gain goes to infinity, right? So limiting value of VE when GH tends to infinity, it's 0. Right? So the loop imposes this condition of if loop gain goes to infinity, the error voltage has to go to 0. right? So if the error voltage is not zero, what is going to happen is, if this voltage is not zero and the loop gain is infinity, then V naught will essentially become infinity, right? So assuming the loop is stable and the output is finite, right? So if you only consider this constraint, let's say you have this constraint, and I tell you that V naught is not infinite, but let's say this, whatever the gain that we have here, this is infinite, right? So let's assume the gain is infinite, and V naught is supposed to be some gain times V1 minus V2. Okay, and I tell you that V naught is finite, but A is infinite. What is the only constraint? What is the only possible scenario? V naught has to be equal to V naught, V1 has to be equal to V2, right? So this is equivalent to that. But who is setting this condition? Because you have a loop around, that loop is setting the condition. This mathematical condition is getting set by the loop. Okay, and the mathematical explanation is this. If you impose GH to tends to infinity, the error voltage goes to zero. The intuitive explanation is, in order to have a finite output voltage under the condition of infinite gain, right? So it's equivalent to the case of something multiplied by infinity is equal to finite, which means that something has to be zero, right? Which with that something is error voltage, the error voltage has to be zero. Okay, so this is vital because most of the circuits that you will see will not be apparent in this form, nice form of G, H, A, K, all those things. So you'll have to find a framework to figure it out. So this is the framework, right? So set the loop gain to infinity. Then naturally the error voltage will go to zero, and then from there you can figure out what is H. Okay. This is also crucial because in when you design anything, you will never get infinite gain. But you should know what is your target. So you might gain a gain of 100, 1,000, million, but it will never be infinity, right? So what should you check to figure out whether your circuit is operating properly or not? So you have to go back and check the error voltage. Each time go back and check the error voltage, right? So as you will see that if you increase the loop gain, the error voltage should keep on reducing. Okay, so that's one of the hallmarks of a well-designed negative feedback network. Did that answer your question? Okay. Okay, fine. So now let's proceed. So there is one more variant of this negative feedback network. So in this network, we have nicely assumed that there is a single loop and everything can be expressed in this format, right? So it's not always necessary that you will have a single loop. And it's not always necessary that you will be able to express everything in this format where there seems to be no direct path between the input and the output. Everything is going through the loop and finally going to the output, right? So a slightly more generic way of expressing a negative feedback network is this. We have a direct path between the input and the output. Let's call this some other name. Let's call this AF. Okay. F stands for forward path. Okay. So if we express our feedback network in this format, what will be V naught over Vi? So we'll do the same thing. If this is V naught, this is H times V naught. This is Vi minus H V naught. So this voltage becomes G times Vi minus H V naught. So your V naught becomes this plus the forward path, right? So Vi times AF plus G Vi minus H. So for V naught over Vi becomes this term, which is the familiar one, and the additional term, which arises because I have a forward path. And this I can express as our traditional form of L plus 1 by L. This becomes 1 plus L. Okay, so the reason we again write it in this format is because looking at this expression, what would happen if L tends to infinity? V naught over Vi will be 1 over H, right? So regardless of whether you have that extra forward path, it shouldn't play any role if the feedback network is well designed. By well designed, I mean L is very high, much larger than 1, right? So intuitively, does it make sense? So let's do that. Let's look at the network once again. Now I have a forward path. So if the loop gain is infinity, again, what is the test? VE is 0. So this is Vi. Then this will be what? Vi by H, right? So as you can see, if the loop gain tends to infinity, the only thing that matters is how this guy is behaving, right? By how the input of the error amplifier is behaving, right? It doesn't matter whether you have something connected through here. It doesn't matter if you have another input from somewhere, not here inside the loop, sorry. If you have another input from somewhere, because everything is immaterial kind of, isn't it? Because ultimately the loop, it seems like the output is being set by the feedback path. Output is not being set by the forward path, right? This is another crucial part of a negative feedback network, that in a negative feedback network, in a properly designed negative feedback network, the output is, you can always figure out the output by what is connected in the feedback path, right? It's not, even though the output is being driven by the forward path, the value of the output doesn't depend on the forward path. Does that statement make sense? Again, a very important concept to grasp, because again, when you will be designing, what will the traditional thing that we tend to believe is this, right? Forget about circuit in anything, right? So let's say I know that I take some action, and this is some block, and this is the output. This is the input, this is the output, right? So forget about output. Let's say input. Let's say I know this is the output, and the output is driven by some block, right? And maybe I have some tapping here and something is going on here, I don't know. But intuitively, always what we tend to think of is, if I have to change the output, I have to change this block, because that block is driving the output, right? That is the general intuition always. But this intuition fails in a feedback network, because if the feedback network is working properly, if you increase the gain of this by factor of 2, factor of 4, it doesn't matter. The feedback output voltage will be set by this block. Okay. So again, when you will be designing, keep this in mind, right? Ultimately you will have, I mean, if I draw this network, it will become extremely apparent. All of you are familiar with this. So even though V naught is being driven by the op amp, the voltage value of V naught doesn't depend on the gain of the op amp to a large extent, as long as A is very high. It depends on whatever is connected across the op amp, even though op amp is driving the output, right? So if we have to increase the closed loop gain by a factor of 2, increasing the gain of the op amp by a factor of 2 will do you no good, right? So it's equivalent to that. So you have to find out what is the knob that is setting the output and change that knob, right? So in a feedback network, the forward path is not the knob. Forward path has to be sufficiently high gain. Beyond that, it loses any value. Okay, fine. Okay, so the another reason we express the V0 over Vi in this format is because it's not always possible to ensure that L is very high, right? So if L is not very high, if L is comparable to 1, for example, then V0 over Vi will also depend on the forward path. Okay, so in that case, we need to figure out again, I have to find out a framework using which I can figure out what is the expected output and what is the output due to the forward path. Correct? So so couple of nomenclatures. So V0 over Vi is 1 over H. So this guy is easy to figure out because if I set the GH to infinity or L to infinity, so whatever I get is 1 over H. So this often is called H infinity. I mean, don't confuse this H with this, but this is a closed loop transfer function, often popularly abbreviated as H infinity, where infinity means that loop gain tends to infinity. Okay. So, but if you have to figure out what is AF, right? What is the forward transfer function without the loop gain? So then obviously, I mean, from this framework, it doesn't seem very apparent what we should do. So experimentally, if I have to figure out what is AF, what should I do? Just like I said, GH to infinity, to find out H infinity, I need to find out what will be AF, what will be this experimentally, what should I do? L tends to 0. If I set L tends to 0, then this guy, so setting L tends to 0 can be done in one of two ways, right? I can set G to 0 or H to 0. So which one should you set to 0? G, not the H, right? If you change the H, then the other guy also gets affected. So you have to set G to 0, right? So essentially, when G tends to 0, whatever you get, we call H naught. Right? So H naught is that transfer function when the forward gain is 0 through the feedback network. Essentially, this. So when you said GH tends to infinity, this is fine. This we understand. We have discussed this quite a number of times. But what about H naught? For H naught, all we are doing is we are setting G to 0, which means this goes off. If this doesn't exist, then obviously the feedback network in isolation cannot do anything, right? So whatever output you get will be V0 times Vi. V0 equal to AF times Vi. So the ratio of V0 by Vi will be AF. Okay. So this is another circuit design hack to establish which is what. So the reason we are doing all those things, and you might wonder that why are we spending time on this? Because ultimately I can always write KVL, KCL and get a big expression. But the key thing is to figure out what to do with that expression. So which means that we don't want to write KVL, KCL all the time for every small thing. We need to look at the circuit and figure out if I can write the transfer function straight away with minimum calculation, right? So these are the ways of intuitively understanding how the network is behaving. So if I can figure out the loop gain should be straightforward because it's an open loop system. Finding a transfer function of an open loop system can be done more or less at one shot. You don't have to write multiple sets of linear equations and then calculate. So which means that I know L easily. I know 1 over h or h infinity also easily, intuitively, because if the feedback network is working fine, V tends to 0, walk backwards, whatever you get will be h infinity. I should also be able to find h naught easily, because if I can identify whatever is the forward path in the feedback network, all I need to do is set that to 0, and whatever output I get is a h infinity, h naught. Okay, fine. So since we are talking about these things in a very abstract way, let's take a concrete example and get cracking, right? Okay, so let's say I have a feedback network, which is A. So from whatever we have done till now, the only amplifier we have done is a common source amplifier, right? So let's replace this guy with its common source equivalent. So a common input is the gate, right? So this is VG. And this is your common source amplifier. Let's ignore the channel length modulation for the time being. Or if you don't want to ignore, we can put it back, right? So let's put it back, we'll ignore later. So this guy becomes GM times VG, and this is some ROUT. Okay. So what is the first test that you need to figure out? The first test you need to figure out is whether the sense of the loop is right. Is it a negative feedback loop or a positive feedback loop? So what will you do? Can you do your analysis and tell me whether it's a positive feedback or a negative feedback loop? And if yes or no, either way, why do you think so? Yeah, why positive feedback? Right. So exactly. So essentially, I can break the loop anywhere, or you don't even have to break the loop. You assume a hypothetical excursion. If this goes high, this goes low, this goes low, this goes low. I have a negative, it goes through a negative terminal, so it means this will go high. So the loop is reinforcing the excitation, which means it's a positive feedback loop. So which means this is not going to work. Since we are in a block diagrammatic sense, we can always reverse the signs here. Okay, so now it's a negative feedback loop. Correct? Okay. Now let me ask you one more thing. If I instead of applying the input here, right? Instead of applying the input here, let me not apply the input here and apply the input here. And I set this to 0. Is this still a negative feedback loop? Yes, no, yes, right? Because feedback doesn't really care where you are applying the input. The loop is independent of where you have applied the input. Okay, fine. So now what you see that this guy VF, this VG is exactly equal to VF, right? Because the other terminal here it is 0. So VG is equal to VF. Correct? So which means that I can get rid of this guy and connect it directly. Okay. So by the way, what is the error amplifier voltage? What is the error voltage here in this loop? What is VE? It's VG, the gate voltage. The incremental gate voltage is the error voltage, right? It shouldn't surprise us because what is the transistor? The transistor is, the incremental gain of the transistor is GM times VG minus VS. right? It is a difference amplifier, right? It amplifies the difference of two voltages. So when I put that difference amplifier in negative feedback, and as long as the amplification factor is very high, we would expect that difference to go to 0, right? So the error voltage is that difference, whatever it is amplifying. Okay, so in this case, since the source is grounded incrementally, the difference is the gate voltage itself, right? So that becomes you had a question? Yes. It should be input and that voltage if we can express everything in this format. It's not always apparent we can express in this format. The error, right. Error with respect to what? So let's understand here. So in this case, how do you know what is the error voltage? Right. So in this case, the way the feedback system is drawn, there is a distinctive summation block. There is a distinctive block here, and we are doing Pi minus Pi. Okay? But if we think in the broader perspective of the negative feedback loop, the error voltage is the input of the error amplifier. Right? As I said, it need not necessarily be that Pi is applied at that particular location. I can apply Vi anywhere. I might want to break this case into two parts, apply the Vi here. Right? I can break this G into two parts, apply Vi somewhere in between. Right? But as long as I can identify whatever is the main amplification block in the loop, right? So all I have to ensure is, all I have to do in my head is assume that the input to that amplification block will go to 0. Right? So this traditional way of is basically leading you into what a negative feedback system is. But in a broader sense, a negative feedback system works properly if the input to the error amplifier goes to 0. Right? So all we have to find out what is the error amplifier. And if the error amplifier gain is infinity, regardless of wherever I have applied the input, whatever the input might be, the input to the error amplifier will go to 0.
And what it would be input of AF?
Okay. Can the error voltage be the input of the AF? That's a good question. Anybody from the rest of the class can have a crack at it? The question is asking is that can I say that input to AF is an error voltage?
Input to AF is independent of feedback.
Right? Input, see, AF is an open loop stuff, right? It's an open loop. Whatever Vi you are applying is directly coming there. So the loop is not correcting this voltage. If the loop doesn't have any way of correcting that voltage, then it cannot, you change the loop gain to infinity or do whatever you want, the input to the AF will not change. Right? So AF will not be considered an error voltage for this loop. Okay.
If that terminal was connected to that circle, then
between which terminal? This terminal.
This yeah, somewhere.
Okay. This terminal connected here.
Then can we consider error voltage?
No, so this is the input, right? Where you are getting the input from. So this model is changing. So see, there are two things at play in this model. One is there is a loop action which is correcting some error, and there is the forward path which is not a part of the loop. So in general, your circuit need not be always, everything need not be a part of the loop. Something can be not be a part of the loop. So this is essentially a model of that. Right? So if everything were a part of the loop, we need not consider this at all. These are all block diagrammatic models to make our life easier when we have more stuff at play. We like to see if we can reduce the broader circuit into this type of format. That's the only reason we do block diagrams. It's an abstraction. Okay. So, okay, hold on. It will probably become slightly better if we take this concrete example, right? Okay, fine. So by the way, do we agree with the fact that in this case, the gate voltage is error voltage. Fine. So if gate voltage is the error voltage, then what we'll do, we'll use the same framework that V naught over Vi is H infinity L by 1 plus L plus H naught by 1 plus 1 by 1 plus L. Right? So now I have to find out what is H infinity. So what could I do? What is the framework? We assume the loop gain to infinity. We assume the loop gain to infinity, then what goes to 0? Vg goes to 0. In this case, everything is incremental. So this guy goes to 0. This is 0. If this is 0, what is this current? Vi upon R. So what is V naught? This current is Vi upon R. So this voltage will be minus K minus 1 times Vi. Right? I am drawing current out of a 0 voltage. Right? So V naught goes negative. So H infinity becomes minus K minus 1. Okay. So let's see H naught. What will be H naught? So what is the forward path in this case? In the loop, what is the forward path? Ultimately, you have to set that error amplifier to 0. Right? You have to take the error amplifier out of the loop. What is the error amplifier in this case? This guy, right? And what is the amplification? I mean, in a common source amplifier, or in this case, what is causing the signal transmission from this node to this node? This is GM times V. Right? So if I have to break this transmission, all I have to do is set GM to 0. Right? In terms of analysis, all I have to do is to set GM to 0. Do you agree? So if GM becomes 0, then what happens? What is the loop now? So GM doesn't exist. This is R naught. So what will be V naught? So what is VG? VG is this error voltage, but will VG have any role to set V naught? No, right? I mean, we purposefully removed that GM term, which means VG is just another node. It doesn't have any role to set V naught. So essentially, the feedback action is not there. Okay. So what is V naught? V naught is, it's basically a voltage divider, right? So Vi times R naught by R naught plus KR times Vi. So H naught becomes R naught by R naught plus KR. Okay. So what is the last thing? We have to figure out what is loop gain, right? So what should I do? So in order to figure out loop gain, let's resketch the circuit. So we had the input here, but in order to figure out loop gain, input is irrelevant. I can desensitize the input. So Vi goes to 0. So what is the next thing? Pardon? Apply a TS, before applying a TS voltage, I have to break the loop. Right? So I have to break the feedback. Not break the feedback by desensitizing GM, but I have to break the loop and apply a TS voltage. Right? So let's break the loop here. And apply a TS voltage and find out V return. Okay. So what will be V return? So if this is V test, then what is V naught? This is minus GM V test times R naught parallel KR. Right? And V return will be 1 over K of that. It's a voltage divider. So V return will be minus GM V test like this, which means what is loop gain? V return over V test negative of that, which is GM times R naught parallel KR over K. Right? So now you have all three terms. You have H infinity, you have H naught, and you have L, all without writing too much of KVL, KCL, and everything. Okay? Yes. Okay. So let's again, that's why this block diagram is useful, right? So in order to find H naught, if I set Vg is equal to 0, what am I assuming? Or V equal to 0, what am I assuming? I'm assuming the loop is in place, right? So loop is in place and loop is working perfectly. Right? So if V equal to 0, what am I supposed to get? I'm supposed to get this stuff. Right? This is 0, which means that this transfer function is the dominant one. And if this transfer function is setting the output. Correct? But I want this. So if I want this, then I have to set this to 0. Right? So it's equivalence between these two. That's why the block diagram helps make the point. Now, is it a bit clear? I see a lot of you are nodding with a lot of uncertainty. So let's spend some time on this. So what is unclear? It's okay, uncertainty is good, but needs to be clarified. Unclarified uncertainty is not good, right? We don't need that forward path per se, but as it turns out, not your circuits doesn't really bother what you need. So your circuit will be something, you have to break it up into some way so that you can model it with something that we understand easily. Right? It's an abstraction that we are trying to put our head, wrap our head around, right? So, so if, for example, if I had applied, if we could express everything in this format where AF is equal to 0, right? Let's say this is not there. Then it doesn't matter, right? Then AF forward path is immaterial. But as it turns out, you cannot. In most practical circuits, there is always a forward path, and not by forward path I mean the feed forward path. This is called a feed forward path. Normally, the forward path refers to this. So the path that is kind of largely that is not getting affected by the loop gain if the loop gain is low, right? So this path is the expected action. This is the expected loop. The expected loop should work properly because that is what we are designing for. But when you design for something, it need not necessarily be that is the only path that exists. There can be some extraneous paths. So what happens to those? We need a framework to analyze. So that essentially is the H naught. It is modeled as H naught. Okay, it's not as if we need that, but we cannot do away with that also. So an example was the one that we just talked about right now. If I shift the input from So in this case, the input was here. All we did in this case, H, we split it up into register divider and applied the input here. Because we applied the input here, the V naught became non-zero, even if the feedback is absent, even if G is absent. Right? So that is in a sense the requirement of the model. Just that you cannot get away with it. Okay. Okay, makes sense? Yes.
Forward path,
Yes.
we can break it from below
okay, good question. If I take it here, right? So that's why I asked you this question that setting GH to 0 can be done in one of two ways. You either set G to 0 or H to 0. Right? So, but if I want to get this term, I understand L should be set to 0, but should I set G to 0 or should I set H to 0? Right? Because if I set H to 0, then this term gets affected. So breaking setting H to 0 is not particularly a good idea then. Right? Breaking the feedback path is not a good idea. You mean here?
Can we break below K minus 1R?
You mean here? Okay. So this is equivalent to what? This is equivalent to tampering with this path. Right? So you don't want to tamper with this path. All you're looking forward to is setting G to 0. Right? So what is the main error? What is the main component of the error amplifier? You set that to 0. So all you see, in principle, all I'm trying to do is to break any transmission from VE to V, from the other side of the G. We are assuming this is a unilateral element. There is no transference of information from this side to that. All we have to then do is set this to 0, set G to 0. So what is that G? G is in our case, if it's a common source amplifier, G is GM times something. I don't know what is G. But G, I know, is proportional to GM because if I set GM to 0, the forward transmission goes off. Right? So I'm setting GM to 0. Make sense? If you do more examples, it will make sense. I'll post assignments you can familiarize yourself with. But very important concept. Again, I am reiterating. So please spend some time on this and familiarize yourself with this. Yes.
So you look at VI by R is the current that is moving upward direction.
Yeah.
And you calculated V naught is K minus VI.
Yes.
Can't we just use that voltage divided through R naught present in like that VG is equal to 0.
Correct. VG is equal to 0. Yes.
VG is 0. That's the current that is going through 0.
Okay, but when we are okay, good question. Yeah, I probably missed emphasizing this fact. So when we are assuming the loop gain is tending to infinity, so what are we assuming on GM? No, GM, how do you, when we say loop, okay, let's do this loop, look at the loop gain term. Loop gain term is this. Okay. Now you want to set loop gain to infinity. What will you do to set this term to infinity? You have to set GM to infinity. Correct? So if you set GM to infinity, this is 0, then you are essentially saying 0 times infinity is something. Right? So that's where the problem lies, right? So that's why that is the main reason why you don't analyze the feedback network in the forward direction, because you cannot come up with a consistent output, because 0 times infinity can be anything. What is that anything is determined by the feedback path. Okay, good question, very good question. Make sense? So again, this is a very common mistake people do when we first start off with feedback network. We always try to analyze in the forward direction and get stuck, right? So don't analyze these things in forward direction when the loop gain is infinite. or tends to infinity, or you expect it to be very high, and so on. Okay, fine. Fine. So let's what I'll do next is show you. I mean, draw a more palatable version of this circuit, and you will immediately recognize. You have seen this circuit multiple times. You'll immediately recognize what this is. So this is a GM. So which means this is a transistor. And in presence of channel and modulation, you have RDS, VG. And apply VI here, right? So this is the drain voltage. This is K minus 1 R. This is R. And the feedback is between drain and the gate, right? So what I will do is I will not sketch it in this way. Okay. And this obviously is a small signal because we don't have any biasing. So if we have to bias, then we have to probably apply some VDD through RD. And we have to bias the gate also. We can simply do this. Okay. So in this case, okay, instead of doing this, let me ask you this. What is the problem if I just simply connect the input like this? If I am taking biasing into account? So let's say I hook up the circuit in this format, and I am taking into account the fact that it has to be biased properly or not. Will this work? What will be the gate voltage? It will be okay. I mean, when I say what will be the gate voltage, I am asking for an approximate answer. I'm not exact. I mean, it's obviously be a function of many other things, right? It will be very small. It will be probably, I mean, one can argue that if RK minus 1R, these are much larger than RT, then, I mean, this voltage will probably be close to 0, right? Or it will not be set independently, in the sense that if the biasing voltage of the gate now depends on bias condition of the input, right? So that is not particularly a good way of biasing. So if I want to set this bias to, let's say, some proper value, whatever that proper value might be. So let's say in the absence of VI, let's say this is not there. So do you think this is biased properly? So what is the gate voltage now? Gate voltage is exactly equal to the drain voltage because there is no current. Quiescent wise, there is no current here. So this voltage is equal to this voltage. So when VD and VG are same, then it's in saturation, right? Because saturation condition is met. Right? Assuming threshold voltage is obviously positive, the saturation condition is met. So this is in saturation, right? So, but I want to apply the input through an R at that node, but I don't want to hamper the saturation condition, which means whatever is the VGQ here, all I need to do is put a battery of VGQ. So then the input doesn't load that voltage. Correct? So now we know instead of battery, I can put a large capacitor. So, so this is a popular configuration. Even more understandable and relatable configuration of the same structure is this. So this guy happens to be a error amplifier, right? It's a transistor, fine, but its main role in this is to amplify the error and feed it back in order to reduce the error, to push the error to closer and closer to zero. So this, in a block diagrammatic sense, can also be thought of as some gain block A with some output resistance R0. And you have this, and this. Right? So let's assume that output resistance is not there for the time being, ideal, everything. So then what is V0? Assuming A tends to infinity. What is V0 assuming A tends to infinity? Minus K minus 1 Vi. Right? Ideal op amps, are you comfortable? Okay, so if A tends to infinity, what happens to this voltage? This goes to 0. This current is Vi by R. So V0 will be minus K minus 1 times Vi. Right? So these two are almost analogous to each other in the sense that you don't have an ideal op amp, but you have a transistor. So if everything works properly and the loop gain is infinity, loop gain is very high, loop gain is this. If the loop gain is very high, then V0 will be minus K minus 1 times Vi, and Vg will be, incrementally, Vg will be 0, right? So this will be 0. So in other words, visually, this is what's going to happen. Let's say you have an input Vi, which is a sinusoid. The output, if K is, let's say, more than, obviously it has to be more than 1, otherwise it doesn't make sense. So the output V0 should look like inverted version of the input with amplification. And Vg will be 0, but it will not be exactly 0 because loop gain is not exactly infinity, but it will be a reduced version of the input in terms of swing, right? The error voltage is Vi by 1 plus loop gain, right? So again, if I go back to this model, error voltage is Vi by 1 plus L, correct? If loop gain is very high, which means the error voltage swing will be 0, but now we cannot, if we are particularly bothered about how small it is, we cannot always assume it to be 0. It will be a reduced version of the input swing. Maybe if the loop gain is, let's say, 10, right? If the loop gain is 10 and the input is, let's say, 100 millivolt peak to peak, your Vg will be 1 by 11 times 100 millivolt, which is approximately 10 millivolt, right? So this will be some 10 times smaller than the swing at the input. Okay, makes sense? Now, note that this is great because of multiple reasons. One, this output, if the system works properly, is dependent only on the ratio of the feedback transistor and this feedback resistor and this resistor, right? Which means it's kind of independent of GM, which means kind of independent of ambient condition variations, right? Good thing in an amplifier, right? You take the amplifier anywhere in the world, it should work properly with a gain of minus K minus 1. Okay. It's kind of independent of RD if the gain is very high. It's also kind of independent of if they have an RL here. Because if you put an RL there, what's going to happen? The loop gain term is going to get affected. But as long as you ensure that the loop gain is much higher, then the circuit operation doesn't get hampered. How do you ensure the loop gain is higher? you have to ensure loop gain is higher by ensuring that the value of GM is high. In this case, GM is the only control that you have. RL is typically not in your control, and R and K minus 1 R probably will be in your control, but the direct control that you have is the value of GM. Right? So you bias your network in such a way that the GM is large enough. So you can get V0 to be kind of independent of RL as well. Right? So these are the two conditions we had set out for. Right? Initially, these are the two conditions we had set out for. The other good aspect of negative feedback is that we didn't set out for, but we are getting that you can appreciate readily, that the swing at the input of the error amplifier is reduced, which means that the nonlinearity of the error amplifier will not affect as much, right? Because what is the nonlinear term proportional to its VG squared, right? It's VGS minus VT whole squared. So you get a quiescent term plus a linear term plus a nonlinear term. And the nonlinear term is proportional to the square of the VGS. In this case, the VGS is dropping. VGS is dropping by the factor of the loop gain. If you increase loop gain by a factor of 2, VGS goes down by a factor of 2, which means the circuit becomes more and more linear. Right? So negative feedback reduces nonlinearity in a nonlinear network as well. So in a common source amplifier, if you apply a 100 millivolt input directly, the VGS, the 100 millivolt directly is applied across the VGS. Correct? So as I'm trying to allude to is, so let's say I can get an open loop gain of K minus 1 by setting the GM times RL to be K minus 1. Right? That I can do. But let's say I apply an input with a bias, and this goes like 100 millivolt peak to peak. This 100 millivolt peak to peak directly appears across VGS. Since it directly appears across VGS, our current, the incremental current that I am going to get will be, or the total current that I am going to get will be some mu n Cox by 2 W by L VGQ minus threshold voltage plus VI whole square. So I am going to get a VI squared term. And since VI in this case is 100 millivolt, the nonlinearity will be substantial. But in this case, VI is 10 millivolt, assuming loop gain is 10, which means nonlinearity of this circuit will be much, the linearity of this circuit will be much better. Nonlinearity will be reduced. Okay, so a very good consequence of negative feedback is it linearizes your network as well. It's all good things. Okay. Any other questions? Okay. So now, before we close, tell me one more thing. Let me draw this. So without doing any analysis, can you tell me, do we have any high impedance node in this network? When I say high impedance, I mean of the order of GDS, of the order of RDS. When I say low impedance, I mean of the order of 1 over GM. Because normally, I mean, those are the two boundaries in which we operate, right? GM times R is very high, which means R is high on 1 over GM is low. VG is a high impedance node. Why do you say so? When I say high impedance node, what am I assuming? If I apply a test voltage, I should get a very low test current. That's what high impedance means, right? Or if I apply a test current, I should get a very high test voltage. Right? So, which means if I inject a current somewhere, I should get, if there is a high impedance node, if I inject a current somewhere, it should create a lot of voltage swing. If I inject any current in the loop, it should generate a lot of voltage swing at that node, right? then only I can say this is a high impedance node. Does that statement make sense? Impedance is V by I. If I inject I, then output should be V times the impedance. If the impedance is high, then for a small current injection, I should get large voltage excursion, right? So without knowing anything about the details of the circuit, can you tell me, in general, can we have a negative, in a negative feedback loop, high impedance node? Let's say so block diagram. Can we have a high impedance node anywhere in the negative feedback network if I inject any excitation anywhere? Assuming the loop gain to be infinite, very high. So let's say I inject something here, right? If I inject something here, what's going to happen? If the loop is high, the loop gain is high, then what's going to happen? This guy and this guy will track each other, which means output will be as is. If the output is as is, this guy shouldn't move, isn't it? Which means even if I inject a current, the voltage shouldn't move. Right? The loop should always correct. That's why there is a loop. The loop corrects any excursions anywhere. Which means that in a negative feedback loop, in a properly working negative feedback loop, there should not be any high impedance. Right? Because that's what a loop is supposed to do. A loop is supposed to always hold the output to your desired value. Whatever happens anywhere in the loop, it should not let go of that output. Which means you do anything inside the loop, if the loop gain is high, the loop will do anything in its capacity to correct the output. Okay, so it will pre-distort something, change something somewhere, but it will always ensure that output is whatever it is supposed to be. Right? So you inject anything anywhere, the current should get absorbed without excursion of any voltage. Right? So that should become apparent from this network also. Where did I sketch the full one? Didn't sketch it. Okay, let's consider this. In this network also, so let's say assume I inject something here. This voltage goes up. What happens to this? It goes down. Since this is coming back, it is trying to reduce that excursion at the gate voltage. Because you have feedback. In an open loop system, you don't have feedback by definition, right? So here you have this node, you inject something here, the feedback voltage will come and action will come and try to reduce that excursion. You inject something here, if you increase this voltage increases, this will try to pull it down. You try to do anything anywhere in the loop is working properly, it will try to nullify that excitation. Because all it is trying to do is to hold V0 to be minus K times Vi, and for that, only thing it knows is to ensure that the error voltage goes to zero. Okay. Okay, fine. We'll stop here. We'll start in the next class.